Let us derive the stiffness matrix, element stiffness matrix for a bar element, one-dimensional bar element. It consists of two nodes and having 1 degree of freedom at each node. So this is the element. 1 and 2 they are the nodes. Q1 is the nodal displacement at 1. Q2 is the nodal displacement at 2. And U is the displacement at any point on the element. So using the natural coordinate system, we know that zeta is -1 at node 1, zeta is +1 at node 2, and the global coordinate system x is measured from the reference axis. x1 is the distance from the reference axis to node 1, x2 is the distance from the reference axis to node 2. So you know that x2 minus x1 will be the length of the element Le. Now this stiffness matrix is derived from the concept of strain energy. So strain energy for a one-dimensional bar element, it is given by this. U is equal to U is the strain energy, half into integral over the length Le sigma transpose into epsilon into A into dx. So here this A into dx is nothing but the volume. So sigma is the stress component, epsilon is the strain component. So this can be derived. So strain energy for a one-dimensional bar element can be found out using this expression. So now what we have to do here is we have to find out the expression for the strain energy by substituting and simplifying for sigma, epsilon and dx. So those three we have to substitute now. So in the earlier lecture I have proved that earlier video strain is equal to B into Q, that is strain displacement matrix multiplied by nodal displacement matrix, and stress is equal to Young's modulus multiplied by the strain matrix, and the relationship between natural coordinate and global coordinate is this. So from this you can always prove that this dx will be equal to Le by 2 into d zeta. So by differentiating this with respect to x, you will get 2 by Le. So where Le is this x2 minus x1 is nothing but Le. So dx is equal to Le by 2 into d zeta. So this is the expression for dx you can substitute. Then for sigma you can substitute this. For epsilon you can substitute this. Now substituting 2, 3 and 4 in 1, you will get an expression for strain energy. U is equal to half into integral. So here sigma is E into B into Q, E into B into Q, all these are matrices, into epsilon, transpose of that, into epsilon is B into Q, into A will be there, into for dx Le by 2 into d zeta. So here, since the variable is changed now from x to zeta, if you are using x, you have to integrate over the length Le. Since we are integrating with respect to zeta, the limits will change to -1 to +1. See here, -1 to +1. Now, from the matrix algebra, so this is nothing but EBQ whole transpose is nothing but Q transpose into B transpose into E. E is a constant here, Young's modulus, modulus of elasticity. It remains the same, whereas it will be in the reverse way. So QT, BT, E into BQ is there here as usual, into A, into Le by 2 d zeta. Now here, what are the constant terms that we can combine together? Half into, so here this Q is a constant matrix because it represents the nodal displacement, which is a constant vector. So QT we can take it outside. So E, A, Le by 2 is constant once again. Young's modulus, cross-sectional area of the element and length of the element being constant. So whatever is left out is integral B transpose into B into d zeta into Q. I can write it separately outside. Now why I have done like this is, this term from here to here, this term is nothing but the element stiffness matrix of the bore element, which is denoted by KE. So U is equal to half into Q transpose into KE into Q. So this KE is nothing but this one. EA LE by 2 into integral -1 to +1 B transpose into B into d zeta. So now what we have to do here is for this beta, for this B strain displacement matrix, we have to substitute, and then if you simplify and integrate, you are going to get the element stiffness matrix for the bore element. Now we have proved in the last video that the strain displacement matrix for a bore element, two-noded bore element, it is 1 by LE into -1, 1. So that you have to substitute now. So therefore, since B is this, transpose of that will be BT, which is 1 by LE into -1, 1. So that row vector will become a column vector. Now, if you multiply this B transpose by B, so which we require here, B transpose is this 1 by LE into -1, 1. B is this 1 by LE into -1, 1 like this. So if you multiply, you are going to, this is a 2 cross 1 matrix. This is a 1 cross 2 matrix. If you multiply, you will get 2 cross 2 matrix. So 1 by LE square, it becomes 1 by LE square into, so if you multiply 1 into 1, -1 into -1 will be +1. So -1 into 1 will be -1. Then 1 into -1 will be -1. 1 into 1 will be +1. So this is the matrix you are going to get as the product of B transpose and B. Then substituting this B transpose into B in this equation 5. So you are going to get the expression for element stiffness matrix for a two-node bore element as EA LE by 2 into integral -1 to +1. So the B transpose into B. So this product is this 1 by LE square into 1 -1 1 d zeta. Now you can see that here this entire thing is a constant. 1 by LE square, 1 -1 1 is a constant. You can take it outside. So LE square gets cancelled with 1 LE here. So you will be left with EA by 2 LE into 1 -1 1 you can take it outside. Integral only in integral d zeta you get. So this integral d zeta between the limits -1 to 1. So integral d zeta is zeta itself between the limits -1 to +1. That's what I have written here. Then if you substitute the upper limit and lower limit, so it becomes 1 minus of -1, which becomes 1 plus 1. So that 1 plus 1 is 2 here. That 2 cancels with this 2. So it will be left with finally EA by LE into 1 -1 -1. So this is the element stiffness matrix for a two-node bore element. This you have used in the matrix analysis of structures also. For a truss element or a bore element, we have used the element stiffness matrix as EA by LE into 1 -1 -1 in the local coordinate system. So this is how we can derive the stiffness matrix for a bore element, one-dimensional bore element which has 2 nodes with 1 degree of freedom at each node. So Q1, Q2. So from the strain displacement matrix, you can always derive the stiffness matrix for a given element.